Let's look at the definition of extrema. Let f be a function defined on an interval I containing a value c. F of c is the minimum of your function on the interval I when your function value at c is less than or equal to the rest of the x values for all those x values in an interval. F of c, which is the function value when x is c, is the maximum of your function on the interval when f of c is greater than or equal to f of x for all the other x's in your interval. The minimum and maximum of a function on an interval are the extreme values, or extrema. The singular form of extrema is extremum of the function on the interval. The minimum and maximum of a function on an interval are also called the absolute minimum and absolute maximum, or the global minimum and global maximum on the interval. Extrema can occur at interior points or endpoints of an interval. Extrema that occur at the endpoints are called endpoint extrema. Let's look at some diagrams. In this first picture, we have a parabola drawn. All three of our points that are highlighted are closed, meaning that these are well defined. The lowest point of all on the graph is where c equals 0. The rest of these are well defined. The maximum occurs when x is 2. If the endpoints of the interval are defined points, then you have a closed interval and you will have brackets. This function is continuous, passes the vertical line test, that's part of our function definition, and is closed. In this graph, our endpoints are not defined. This point and that point are not defined. This minimum point is still defined. It is closed in when x is 0, the y value is 1. In our notation at the beginning of the video, this would be considered c, and this would be considered f of c. Since the endpoints are not defined, the function is continuous because you could still draw it with one without lifting up your pen or pencil, but we use parentheses on the ends, and that's considered open. This function is considered piecewise because the point that used to represent our minimum is not defined at the bottom. This highest point is defined, and because this minimum point is missing, this is called a piecewise function because you still have the graph of x squared plus 1, but the problem is when x is 0, you have a different function value. This point that's defined is 0, 2. That's the other piece of this function. So you have the graph of x squared plus 1 everywhere except where x is 0. This is closed. Our endpoints are well defined, but we can't claim that's a minimum because that point at the bottom is not defined. The point at the top here is. Some more definitions. If there's an open interval containing c on which the function value f of c is a maximum, then f of c is called a relative maximum, or f of f, Or you can say that function f has a relative maximum at the point c, f of c. If there's an open interval containing a value of c on which the function value there is a minimum, then f of c is called a relative minimum of f, or you can say that f has a relative minimum at the point c f of c. The plural of relative maximum is relative maxima. The plural of relative minimum is relative minima. A relative maximum is sometimes called a local maximum, and a relative minimum is sometimes called a local minimum. Let's look at figure 4.2. This function has a relative maximum at the origin. You can spot the hilltop, and a relative minimum at the point 2, -4. So relative maximum occurs at the little hilltops. Relative minimum, or minima if there's more than one, occur at valley floors. The value of x at a hilltop or valley floor is called a critical number. Let's look at that definition. Let f be defined at point C if the derivative of your function at C is equal to 0, or if f is not differentiable at C, that just means your derivative is undefined, then C is called a critical number of your function. Relative extrema only occur at critical numbers. If f has a relative minimum or a relative maximum at the point x equals c, or where your x value is equal to c, then c is called a critical number. We have some guidelines for finding the extrema of a continuous function on a closed interval. And in Google Drive, you can access these documents at any time. If you want to print these off until you get comfortable with the steps, please do so, or you can just refer to them on your computer or device, phone or iPad. To find an extrema of a continuous function on a closed interval, what we'll basically do is we're going to find the critical numbers of f in the interval. So that's taking the first derivative, finding out when it's equal to 0 or undefined. We'll evaluate the function at each critical number, and then we'll evaluate the function at each endpoint. The least of these values is the minimum, and the greatest of these values is the maximum. Let's go into some concrete examples and see how these relative maxima and minima play out with respect to derivatives. Find the value of the derivative if it exists at the indicated extremum. Remember, that's singular form. For this function, we have x squared over x squared plus 7. The graph of that is over here to the right of your screen, and it basically looks like an upside down bell curve. When we take our derivative, because this function is a quotient, we're going to use quotient rule. Derivative of the top times the bottom minus top times derivative of the bottom, all over the denominator squared. Distributing across the top, we get 2x cubed plus 14x minus 2x cubed. Our 2x cubes cancel. That leaves 14x over x squared plus 7, quantity squared. In a fraction, because our derivative is in fraction form, you can have cases where it's equal to 0. That's when the numerator is equal to 0. 14x equals 0 if x equals 0. So our first derivative is equal to 0 when x is 0. Your denominator can also be equal to 0. However, this one does not. If we take x squared plus 7, quantity squared, and we set it equal to 0, when we square root both sides, we get x squared plus 7 equals 0. If you subtract 7 and take the square root, you end up in a complex number. Turns out there's no real numbers that can make your denominator 0. That's information. That just means that your derivative is always well defined. The numerator, note here at the bottom of this curve, the x value is 0. At the origin, our function has a horizontal tangent line. If we investigate the derivative at that x value of 0, in our notes from the previous slide, that's called c. That's our c value. F prime of c, 14 times 0 over 0 squared plus 7, quantity squared, that's 0 over 49, which is 0. That's something you'll always find true. If you have a smooth curve, wherever it has a hill or a valley, the x-coordinate at that location, when substituted into your first derivative, will always give you a value of 0. And because derivative is rate of change, horizontal lines always have a 0 slope, and that's why that goes hand in hand. Let's change to a different function. Sorry that some of this is blending onto other functions. Probably should have spaced better. Hindsight's always 20/20. For this function, we have f of x equals cosine of pi over 2x. Its graph is provided here to the right of your screen. When we take the first derivative, we're going to have to be careful to use chain rule. The derivative of the outside function is negative sign. We leave the internal function the same, times the derivative of the internal function, which is pi over 2. This is a product, so I'm moving pi over 2 in here just to get it away from that angle. Let's note on our graph that when x equals 0, we're at the top of a hill. That's a horizontal tangent line. Let's also note that at the bottom of the valley, we have a horizontal tangent line when x is 2. If we take our first derivative and substitute in both of those critical numbers, when we sub in 0 into the derivative, we get negative pi over 2 times sine of pi over 2 times 0. Sine of 0 is 0 times negative pi over 2, also 0. Let's go to the other critical number when x equals 2. F prime of 2, that's negative pi over 2 times sine of pi over 2 times 2. Those 2's cancel. Sine of pi is 0. Negative pi over 2 times 0 gives us 0. Any critical number subbed into your derivative will equal 0, provided that your graph is smooth. Not all graphs are smooth. Some have sharp turning points called cusps. You can also call it a kink if you like. That's this last example. Sorry that bleeds into the problem at your upper right. Let's take the function x plus 7 to the 2/3 power. Its derivative, we're going to have 2/3 x plus 7, take 1 off your power, negative 1/3. The derivative of the inside is 1, so we've done chain rule to take that derivative. Let's leave the 1 times 2. Let's leave the 2 in the top. The 3 is already in the denominator. If we move this term back to the denominator, our exponent goes from negative to positive. The numerator is never 0 because it's always 2. Well, notice here on our graph, we don't have a smooth curve. It just comes to an abrupt point. That's called a cusp. Where does that occur? What value of x can I plug into here and get 0? That's right, it's negative 7. So even if it's a sharp point, that's still information. That's a critical number. It just happens to make our derivative undefined. If you take your first derivative and you substitute in negative 7, you will get 2 over 0, and that's undefined. If your graph is smooth, then you'll get 0 for your answer when you plug the critical number into your derivative. If you get undefined, chances are it's a cusp. Approximate the critical numbers of the function. Determine whether the function has a relative maximum, a relative minimum, an absolute maximum, an absolute minimum, or none of these at each critical number on the interval shown. The graph at the bottom right of your screen is not defined at the ends. This is an open graph. At the top, where x equals 1, that's a critical number. It's the only one. Relative and absolute maxima, because we're at a hilltop. Absolute maxima, because that's the absolute highest point in the interval, -2 to 4. But it's also a relative maxima, because there's no other values of x that will exceed this point. F of 1 is equal to 9. F of any other x value is not 9. It is less than 9. Like at f of 0 is 8. F of 2 is also 8. 9 is the largest function value, and it occurs at 1. Because these bottom points are not defined, we have no relative or absolute minima. In this graph, we have, let me try to get that focused a little bit. There we go. We have a graph that almost looks like the McDonald's arches. The ends are not defined, they're hollow points. This one, however, where x is 6, is defined. That graph comes down. Yes, it's a sharp turn, but that point is defined. At the top, both of those points are well defined. The red dots, which occur at the tops of the graph, are when x is 3 or 9. Maybe and's the better conjunction. At the bottom, that point is defined, and it's at the lowest point that graph ever achieves. So this graph has 3 critical numbers, 3, 6, and 9. The relative and absolute maxima occur at 3 and 9. The relative minima and absolute minima occur at 6. We can't say 0 or 12 because those are not defined. Had they been filled in points, we could.